Okay, awesome. Good morning. Yeah. It's,
Making sure no one's still up there.
well, I see people still up there actually,
but
it's not us.
Yeah.
So we started our hike this morning, and it was nice. Mike and Adam came, and it was a beautiful sunset. There were some hot tubbers, not to be named. And we started the hike, and I saw like 4 people down the trail. I'm like, oh yay, more people are coming, but it's fine. I respect everyone's decision.
He says as if he doesn't.
No, it's there's so many good things to do, so it's hard to choose. But I hope you guys are drawing some inspiration from the surroundings, and I've been enjoying the discussion, so thank you. And in the spirit of discussions, both the beginning and the end of my talk are super sketchy, just meant to evoke discussions because I'm really curious for y'all's thoughts. You can probably tell from the titles of like truth and physical basis of human experience that like, I don't know, there's a lot of like big picture things that I'm curious about, that I'm confused about, that I feel like we're starting to get some angle at with this, with kind of tight feedback loop with AI that we haven't had before, which is pushing on intuitions. So maybe we can lean a little bit on that, and also lean on our understanding of physics, pattern, again, kind of what intelligence might be in our universe. And something I've been wondering a bit is this question here of, are concepts in the universe universal? And part of this is wondering, like, what's the trajectory of AI? Like, how would we interact with it? What does it become when it's out of our hands? And it's really hard to think about. But some of the work that I've been involved in with Adam and Sarah and others, that we've started to find something like universality of representations, which seems to be something like architecture independent. Maybe it doesn't matter what your neural network's quite like. Maybe it doesn't depend on neural networks. Something about the correlational structure of data wants to be represented in a certain way. And this kind of gives me some hope that we can see what it would be like to anticipate and interact with other intelligences, but it's a big open question. There's a long ways from here to there. So this is meant to kind of get at various angles of this question. All right. There's a few recent papers that, I'm not going to flash them all up, but a few recent papers that I feel like are relevant at getting towards this question of harkening back to good old Plato. Maybe there's some, I don't know, either reality out there, or maybe it's not even in the physical world, but there's some like Platonic form of like the perfect way of things, you know. So whether you think there's like some Platonic stochastic process from which we're sampling everything, or, you know, there's, even in this kind of simple scenario, there's a red ball and a blue cone, and if different observers were looking at that through different lenses, maybe different linear functionals, I might say, maybe through image, maybe through text, maybe those representations would end up embedded in a similar way. So this paper is kind of nice motivationally saying, you know, and they kind of talk about some of these various results that have shown there seems to be some convergence. So there's some truth out there. Well, what does physics say about truth? Well, if we think about, say, relativity or quantum, we can't actually agree on facts unless we have a shared framework. For example, like, oh, these things happen simultaneously. That's like not a well-founded statement, actually, unless you're talking about a reference frame, and you might just fundamentally disagree. That's why I drew this kind of freshman year physics sort of car in the garage sort of thing, right? Like, one observer, maybe I would say like, oh, the car was fully in the garage at some point. And then someone else is like, no way was the car fully in the garage, it wouldn't even fit, right? It's kind of silly, but it's like, if we're talking about a Platonic truth that we're all representing, maybe you could have some fundamental disagreement unless you had the concept of relativity. But then maybe the framework of special relativity isn't sufficient. I mean, of course, it's good enough for a lot of purposes, but in some situations, actually, we should be talking about general relativistic effects. And so if you don't have that framework, then you're going to disagree. Well, we know that can't be the ultimate theory because of quantum, and they need to be reconciled. So there's going to be some quantum gravity we don't know about. And well, part of my talk later is going to talk about post-quantum theory, and actually neural nets seem to learn something about post-quantum representations already. So I wonder a little bit of if we can come to the same framework. I guess it feels contextual, like we can get away with Newtonian physics, you know, in the sort of everyday setting at our maybe time scale and mesoscale and all this. So I guess if different intelligences are embedded contextually in the same way, they'd probably come up with similar concepts and representations. Okay, so there's a bit scattershot here, but something I'm confused about is can we think of different concepts as, maybe there's some extremal concepts, and then some concepts like are basically like linear combinations of those, or like in the convex hull. Like we were talking the other day, is it Adam saying a kid saw a giraffe and called it a dog, and then it is here, yeah, Alex, yeah, that's right. And I was like, oh yeah, well, it kind of makes sense. It's like a dog with a long neck, and so this is kind of an example of this. Like, well, if you have the concept of, ooh, I'm going to butcher this, dog. And long neck. Right? There's like somewhere in the convex hull of this, there's a giraffe that we're gonna see at the zoo today. Just okay, forget the picture. You get the idea. Mike, feel free to illustrate for me.
Your concept's clear enough.
Yeah, this is embarrassing. So, you know, and then. Maybe there's the idea of color, right? That if you didn't have that concept, how would you explain it to someone? You know, maybe, so that's what I'm thinking is like a very big version of this where, you know, this is kind of the convex hull of all the concepts I have, and maybe this is, well, this is the convex hull of all of the ideas you have, and we have some shared ideas. But are we always going to be talking past each other? Is it possible that you can have a minimal, kind of almost like an autocatalytic set of concepts that would be sufficient to get everywhere? I don't know, something about like Turing machines would, maybe you just need simple stuff to get a lot of concepts, but then
But these are concepts of any type of intelligence, is that the idea? Or
yeah, I mean, I guess like
this isn't concepts of intelligence, right? You
yeah,
mean
no,
concepts
like
that are intelligence
so like
is capable of.
so yeah, in concepts that intelligences are capable of. Like, would they, like, given enough time and resources, like maybe we're just too slow, and like AI or aliens would give up on us or something like this. But like, is it in principle possible to like communicate, or will there sometimes just be like the base concepts are too different and you can't come together?
So the convex hull, we're also remaining in a certain kind of sense of space.
Yeah.
But for what it's
Yeah.
worth, for a long time, computational learning theory used defined concepts as Boolean functions.
Boolean functions.
Yep. So the mid-70s through kind of mid-80s, late 80s, all of that computational complexity of learning was framed in terms of
Yeah, and which feels
people try.
yeah.
They can't
Boolean
get the
functions
Boolean
to me
function.
feels kind of discrete, and maybe we should be looking at a continuous
Well,
space.
they're really computer science folks, so.
And that's actually something I'm gonna get to a bit. Is I think in a lot of things that I'm seeing and feeling with intelligence feels like it happens in some kind of continuous space where it feels like, ooh, maybe information theory isn't quite the right setting, despite some attempts at like information bottleneck and stuff like that. There's something really about the real valued vector space of neural activity, things like that, where it's utilizing the continuity. And so things like convex hull kind of make sense there.
I would say one point is that computers are actually discrete.
Computers are discrete.
The way we model things is discrete. But that is, I think, not a problem for your point, because continuity is not really about like continuous space, but about some sort of error perturbation, which can happen in discrete spaces as well.
Mm-hmm.
You can have discrete things which feel continuous. The computation is always continuous in a sense.
Mm-hmm. And something I'm noticing like with neural nets, like it's implemented on this like discrete computer, but it's utilizing this effectively real value space up to floating point precision. Although then I have questions about like what this quantization does to that. It's a little strange. Yeah.
On the other side, so continuous. It's kind of interesting to me that there's this progression of like computing from originally it's like real valued circuits, and then people are like, oh, Turing machines, we should do discrete computing, and then with that discrete computational set of tools, now we're implementing continuous real values to do computations. But then I was hearing, I think it was Chris Pillar was saying that apparently you can distill the computations of a neural network into basically Boolean logic once again. So it seems like we're sort of oscillating in technology between continuous and discrete valued logic.
So I think that's the point I was trying to make, which is that maybe the final thing can be discrete, but the process which is importantly continuous is how you come to the weights. Like that process has to have some sort of error perturbation. The way you find the weights or do gradient descent over it shouldn't matter too much. It can go a little bit around in that space. There should be some sort of notion of space or error perturbation or error resistance while you're finding the weight, and then maybe you can quantize that.
So it's like you're coarse graining the continuous space. We saw like in your pictures yesterday, like your continuous space had sort of these clumps for these proteins representing discrete configurations.
Mm-hmm.
Yeah, so some of the stuff I'm going to show
Yeah.
is this way in which it feels pretty principled, in which we get to these universal representations, but then kind of what I feel like is the principled part breaks down, whereas your talk yesterday was like, there seem to still be these representations, but at least for me, it's not clear how to get there and find like a canonical version of that. But still, the thing that you're finding corresponds to what like scientists seem to intuit, of like maybe with the separation of timescales, like these are the confirmations that seem to matter.
Well, just to specify that, those different confirmations are actually like extracted from the time space data itself.
Yeah.
You can show, like, we calculated the angle that the molecule is at, which then corresponds to a place in the energy landscape.
Yeah.
So, just to clarify that, like, those were the actual energy states that were found.
Right.
At least in this simulated.
The thing that you found does correspond to those.
Yeah, to the actual energy landscape.
Right.
But I mean, this is a simple example. It's a simulated. It's not real data in the sense of like it's still a model, that kind of thing. So
Yeah.
just give all those caveats.
Yeah.
Maybe this is not important point enough, but do we need an answer to this? Does there have to be one answer?
Well, if it's not answerable, I'd also like to know that. Or if you're saying, or there are different answers and they're
And they coexist.
coexist. Okay. Do you have suggested answers?
Sure, you just look at the system and have a kind of a concept that lets you find out where the information is stored, and it can be discrete, substrate, or continuous, or simulated. And what you want is a tool set that lets you find that information storage and processing, independent of the system's instantiation. Take a look at different systems, and maybe even compare them. So just to say I want a framework kind of prejudices how you're looking, because you're kind of exercise of making these things merge. And most of it's kind of compatibility and kind of conceptual tools that will let you look at the system structure and behavior for what it's doing on its own.
Yeah, I guess I hear you saying something like, let's look at its information processing, and like if we abstract from some of the details, then we can see it, what it's doing. I guess
I wouldn't use the word abstract. I want to know the world on its own terms.
I see.
So to say abstract is to kind of move towards being, and systems are systems.
Right.
Animals are animals. They do what they want, and we've had this issue of mapping, whatever they're storing or processing. Even saying they're processing information is almost too much of an assumption for me.
Yeah.
Yeah.
Right, so I guess a little bit that's like, oh, I want to observe this thing, but then I'm asking something I think
Yeah.
slightly different, which is what would it be like to interact with this thing?
Oh, so different.
And what could the emergent
Mhm.
interactions be,
Mhm.
and is it restricted by what these concepts are if they're universal? Yeah.
Experimental feedback is important.
So I think there might be something like a platonic reality out there with their correct physics framework and basically the different ways of perceiving it. Maybe they're linear functionals of space-time. And I think that could be useful because then linear algebra suggests correct representations or emergent representations.
All hail Koopman.
Yeah, all hail Koopman. So maybe we can work towards super general relativity, where like it's like all concepts are just only gain meaning in their relation to everything else. Everything's relative in a way, but in a way which is meaningful. Like a concept is embedded in a space relative to everything else. So it's very
Does that
sketchy.
relativity sort of say there are no answers in the absolute sense you want to go to? There's no preferred representation? And we just end up with a calculus of, let's just shift from your understanding to my understanding through transformations, okay? But is there a thing out there? No, there's a way of mapping between things or information.
Yeah,
Okay.
maybe what we need is
But I
maybe what we need is like there's a set of maps rather than the objects. Yeah.
I can't help think about causal set theory in context to this, where you have sort of this discrete representation of space-time, which is itself a fixed directed acyclic graph, but that can be interpreted in many different ways. You can kind of project space and time onto it, depending on how you interact with the graph. So it's like there is a ground truth somewhere. It's just maybe our primary experience of it is observer dependent.
And it's not a directed acyclic graph, because that precludes time.
I don't know.
I mean, even without going to like causal set theory, like just with relativity, it's like our version of experience is not like the same as another, even though we're somehow living in that same reality. Like we don't share the same now, technically.
I guess the point I was making is that there is a ground truth fundamental object.
You can choose,
That's
say that.
maybe like a
Seems to be.
preferred reference frame. It doesn't exist, but there is some fundamental object underneath everything that's not reference frame dependent.
Maybe. I mean, it's part of like the question or suggestion. But
You used the word Plato already, so I guess that's the context. And there are other ways of framing this, a single answer. If you need to do your transformation.
Mhm.
That's what relativity is. I don't think that it's going to, after you play with changing between bases, you can get some sense that beyond that, between you and I, there is a notion of these events happen relative to each other. But I don't conclude that that says that there is a single thing out there. It's objective reality.
yeah,
There's
you
a
could
sense
choose
of
to think of it that way, but like whether that's like a physically instantiated thing is not clear to me. So I'll start moving to some maybe more of the technical part of my talk, and then we'll zoom out again, perhaps if we have time, to these confusions about humans. Right, so this is, I think for me, highly motivational, nice paper where they're looking at these, something like universal representations. It doesn't happen to be sequence learning or anything here. This is actually just training different neural nets on MNIST, so like the images of numbers, right? And in this case, it happens to be basically the same network, but you initialize it in different ways. And then what's learned, these are like the classifications, the clusters of different numbers. You can probably see that like 1, 3, and 4 are basically rotations of each other in neural space. And then I guess 2 is kind of like that, but also there's some reflection going on. So there seems to be some universality in representation for this architecture up to linear transformation. This paper is also pointing out, like even across architectures, across modalities, there's some way in which you can kind of Frankenstein different models together. Like even if you had a model trained on visual stuff versus text, you just need to find a linear map that goes from one to the other to rotate the representation, and then you can use the Frankenstein model just fine. So there's results like this, which are reminiscent of also some of the results that we're getting, which seems like it's not necessarily something just about next token prediction. There's something very high level that I'd like to understand, like how our work fits into this broader framework of universal representations.
So the universal is that thing out there. A typical move in mathematics is to talk about a set of invariants that are both groups of transformations, and then what is invariant is the thing.
Yeah.
Okay, so
That's kind of the point. Yeah.
Oh,
Yeah. Exactly.
I can call that.
Yeah. It's like, what's the thing shared between those? What's the invariant there, right? That's the thing, and up to that, maybe it's yeah. So up to linear transformations, there's a thing. In this case, there appears to be this thing up to some, up to something. So what are they? How can we anticipate them? There appear to be these things, but they didn't predict like, aha, this is the geometry up to transformations. They're just like, there appears to be this thing. So can we predict ahead of time what that thing should be? What are they? So we're going to get there. I'm going to give a little bit of background. I don't think I need to give too much because already with Adam and Alex's talk, you guys gave nice motivation on thinking about dynamics, sequences, computational mechanics, and think of belief states in the simplex, the probability simplex of generative states of a stochastic process. So we're going to kind of get there as kind of a reminder, and then I'm going to say something about how, well, there's this kind of quantum version of computational mechanics, which is, if you allow yourself quantum physical states rather than classical states, it turns out that you can produce classical stochastic processes with less memory, less qubits, than would otherwise be classically necessary. Like, otherwise you'd need many classical bits. And I've worked on this stuff a little bit, and I was working on the neural network stuff, and realized that it's not really quantum in a way, the advantage. It's really just that you're in a kind of real value vector space. But neural networks are real value vector space effectively. So then at some point I'm like, this has to be true, this has to be true. And I was telling Adam, like, before we ever ran the experiments, it has to be true. And now we're running experiments and it seems to be true that neural networks learn. Basically, they update their beliefs over what would seem to be quantum and even post-quantum models of the world that efficiently represent their data. So that's kind of where we're going with this.
Are you going to define post-quantum?
Yeah, it's basically like pretty general linear transformations. I'll talk about it later. Yeah, and so kind of what I and kind of we have learned in some of these initial experiments is there's this importance, and this is kind of a lesson from computational mechanics, that predicting is a harder task than just generating behavior. You can act like a human, and you might say, oh, this thing is sentient because it behaves like a human. But we're actually training AI to predict text, to predict humans, and that's already a superhuman task. Like, predicting is way harder than generation, because you not only need a generative model of the world, but need a way to do effectively Bayesian updating over the hidden states of that world model. And we end up finding that neural networks represent these belief states as if they're doing Bayesian updating over a world model. Next token prediction, the standard way of doing cross-entropy loss on sequence data, implies long horizon prediction, which Adam already talked about, that if you had a recurrent state, this is necessarily true, that there's a nice paper from Shalizi and Crutchfield, so Cosma and Jim from 2001. Yeah, sorry about this. But back in that paper, there's this lemma 2 that if you translate it into just modern ML lingo, says that to do as well as possible at next token prediction, you need the ability to predict the entire future as well as possible from the past. If you're basing your predictions on some recurrent state. Well, and then we have these feed-forward networks, so it's a little fuzzy, but there's some kind of framework where this makes sense, and what's borne out empirically is that the models are doing this, and that they effectively get the distributions over the far future, even though they're explicitly trained on next token prediction. So the thing that we're finding is this, this intrinsic structure of data, which has to do with the correlational structure of data, which finds its way into the model. That the representation up to some transformations is due to the correlational structure of the world out there in some sense. So, basics of LLMs, which you guys all know by now, is we're training models to predict future tokens from past tokens. So you type into the prompt of ChatGPT, "Hello world, can computational mechanics help us to understand AGI?" And it chunks up the words basically into tokens, and those tokens get mapped onto some like integer numbers. There's something like 50,000 maybe or more these days. And then each of those numbers then gets embedded into effectively a real valued vector space. Right? And then some series of linear and nonlinear transformations and all this, right? Obviously we know the model's architecture, people build it. Well, we might not know necessarily what the frontier models are doing, but we know like well enough how this stuff works. And despite having access to everything, we don't know much. So it's like, it's early days, we're doing very basic science, we're coming at it from a few different levels, but just from like a scientific research point of view, like it's a wonderful problem, and I feel like it's a very important one to hopefully bring light to the black box. So the kind of framework here is, yeah.
Yeah, so I was just gonna say, I haven't thought about it this way before, but I think it actually doesn't completely fail as a way of thinking about it. So if you guys have heard of Mars levels, there's a computational level, there's a mechanistic level, which is basically what we have for the LLM. We know exactly how this maps since we have like an understanding of how all the molecules interact. The algorithmic level is sort of like, how does it actually get it done? And the computational level is like, what is it doing? It's getting the causal states. That's sort of what the paper was. It got the computational level. And then the algorithmic level is still like, what's going on?
Yeah, I think
It's David Mark, by the way.
Yeah, he has this famous book on this, right?
Yeah.
Yeah, I think that seems like a fair characterization. So maybe that's the level that we're at.
Yeah. Like, it just might be an interesting way of thinking about like AI interpretability to use Mars levels. We have the mechanistic, and we're trying to get the computational, and we're trying to get, we kind of have the computational because we have a loss function, but we're trying to get the computational, like what is it actually kind of doing, and then the algorithm.
So there are some people doing like taking an algorithmic perspective, thinking of various circuits, but part of like this kind of real valued space thing, I'm like, maybe like thinking about circuits in a certain way is not super helpful. But yeah, it's something that would serve as like an algorithmic understanding is what we're working towards now.
Yeah, Mark's first paper on this is very good. Everyone should be done. It's had a huge effect on us on computer science and neuroscience.
Nice. So the way in which we can think about a lot of the world out there that intelligent beings experience and large language models is that the stuff coming at you, you can think about it as a sequence of correlated random variables. And you get pretty far from that. And if you just look at this, forget the embedding and everything, just like, there's some pretty basic questions of, well, okay, I have this text, or I have the images coming at me, how random is it? How predictable is it? How do we actually do the prediction? And computational mechanics has been a really useful framework for figuring this out. I mean, of course, before then, there was just good old Shannon entropy for how random this thing is asymptotically, the convergence to that asymptotic randomness, that we've kind of worked out, and then how predictable, importantly, that's not just the lack of randomness, like these are actually orthogonal concepts. So all these things are kind of worked out in computational mechanics, but then like, how do you actually do the prediction? Something about, if you do have the world model already, then you're going to be doing Bayesian updating over that. How do you get that world model? something about learning theory that we're trying to sort out right now. But somehow the answer to all these questions is got to do with this probability distribution over this joint set of random variables. So just kind of notationally, x1 to L is all of x1, x2 through L. Somehow this contains the answers, and you think of like training data is sampled from this platonic form of like the stochastic process out there, like if we were to sample more data. Yeah.
So you're talking about interacting with the world. Do you have an idea of like a degree of interaction and when you can do interventions and that kind of thing, or
I think part of what I'm getting at right now is how we build up our understanding of the world, which is prerequisite to acting in it in a way.
Okay, so sort of
So-
okay.
So maybe it's not the right way to do it, but we inherit a brain, you're pre-trained, you have these concepts, and then you could choose for it to act, the entity to act and receive feedback and fine-tune that way, but I'm not going to address that head on.
Okay, so sort of like there's a phase where the actions just kind of don't matter, and then that's the phase that you're sort of in, and then afterwards that.
Yeah, and I can anticipate like with AI that basically pre-training is very important to get like an understanding of how everything's interrelated, and then you can also then have these actions on top of that where then things would change importantly, but that's not my focus here. Yeah. Okay, so we have this work with Adam and Sarah here. Was recently accepted to NeurIPS. But before that, it made a bit of a splash on the internet because, well, for one thing, we found fractals in the minds of transformers in the mind of AI. People think that's cool. But I think maybe optimistically, another reason for it is that it went towards answering this question of like, do AI models, do they have a world model? What's the implications of next token prediction? And at least in this toy setting where we have small transformers, toy stochastic processes, we basically find that the answer to pre-training is this belief state updating. And it's, this belief state geometry ends up being linearly represented in the neural activations.
So what do you mean by pre-training?
Yeah, pre-training is, your loss function is minus log of the probability of the next token given a history of some length. And so you just want to predict that next token well given some past. And you do that with like all the data on the internet.
And this is pre-training.
Pre-training, which is all of the compute.
That's the concept I'm not having difficulties on.
Yeah.
Fallback.
Well, so then after that, you can like fine tune it to be like, I don't know, somehow aligned in the superficial sense of you would want to interact with it. Like, so after pre-training, you have this base model, which I would characterize it as it has this kind of understanding of the interrelation of everything in the world, but it doesn't necessarily behave in a way that's useful for you.
Start with some model, and then there's a phase in which you can add the tweak, but the idea is you start with the model, and that's what pre-training is.
You start with, and you have the architecture, then you cram it with data, and it's like $1 billion.
Right.
That's pre-training.
That doesn't sound very mathematically rooted as a concept. It
You
seems
should
like
take that up with
I mean,
other topics.
I mean, you can break things up into training and testing pretty intuitively, but like if you do pre-training, why don't you do pre-training and then pre-pre-pre-training?
No, I mean these are just
It's I mean
It's telling you about how that crowd frames their problem. It's not how you do it. I just consider it.
yeah, they're doing an engineering thing.
Yeah,
They're-
absolutely. It's just.
I think it's reasonable given what they're trying to do.
Yeah. Where am I at time-wise, by the way?
You are at 34.
34?
Yeah.
I think I can maybe just go straight to the quantum stuff because it gives a better explanation. So you heard about HMMs. You can think about these labeled transition matrices. So there's linear operations for, you just have matrices that you can use to calculate probabilities of all your words. And So it's kind of notation, eta nothing here is like an initial distribution over the model, and the probability of any word you can just calculate by multiplying a bunch of matrices. And this is like an all ones vector here. So that's nice, everything's linear algebra, so then you can say the probability of the future given some past word is going to be, well, this is just the probability of the joint divided by probability of the word. But then you see, well, this thing here on the left is just some vector that any word that induces the same vector can't affect the future differently. So just by following the linear algebra, you automatically get this equivalence class where the linear algebra tells you which words are nearby and even which words map to the same effect on the future. So this relation, I think, is quite important. And then you move between different belief vectors here. And that's the metadynamic belief updating that has been talked about. There are these generative models which may or may not be unifilar, and when they're not unifilar, when you do Bayesian updating, you continue folding probabilities in such a way you get something effectively fractal, and you generically get these infinite state. If you're very explicit about your belief updating structure, maybe you don't need to be explicit, but if you're explicit, you can write down this graphical model of that. But then, again, as has been talked about, then there's this geometric embedding of, well, every one of these states is just a distribution over that, so they live in this case, in, well, this vector space is just along one dimension, actually, because also you reduce the dimension because probabilities have to be conserved. So there's some geometric thing, but yeah, so how do you go from there to there? Jadam already talked about. So you have a generative model, you have the kind of automata version of belief updating, and then you embed that, you can think about it as its geometric representation. And I think it's important to realize there's some sense in which this is canonical. It doesn't depend on the generator because of this, that the way that these belief states, like if you take linear combinations of the belief states, that implies the same linear combinations for the probability distributions over the future themselves. So the linear relations you find in the simplex for any generative model must be, any linear structure in this thing must be inherited by this thing. If you have redundancies, you might trick yourself and see more structure here, but any linear relationships here must be represented there. So there's something about distributions over the future live in some vector space. And so there's some like real geometry.
Probably why we use probabilities. You can add things up for probabilities.
Yeah.
When you guys train this, so you're predicting the exact next token, like the actual ground truth is like one token, right? So does it like take the max over the?
No, standard pre-training,
Yeah, but like you're standard pre-training, right, over these like sequences.
Mm-hmm.
But in order to get the best loss, like if one token has like a 6% chance of being next, and one token has a 40% chance, the best loss is to predict the 6% chance token, like with maximal. Like
No, that's on one thing, but right, you do batches and stuff, and so you do cross entropy over that, and then it averages out.
I mean,
Okay.
yeah.
Let me just anticipate, often when we talk, when we say prediction, we mean distribution. We're not, the decision
Yeah.
problem about whether I'm actually committed to heads or tails, we don't think about that too much.
Yeah,
I was just wondering the loss
your,
function.
Your,
like,
your
what-
loss, your loss is
very
minimized.
standard,
Your
yeah.
loss is minimized
Over, yeah, true.
when you get the correct distribution over the next
True,
token.
yeah.
And then there's this other thing where it seems to imply also you need the distribution over all future tokens.
Yeah. Okay, this makes sense.
Yeah, you can think about it maybe as batch training, and then it will kind of even out.
Yeah.
Right. So we have then these experiments that Adam talked about, where okay, you have the architecture, you can find in the neural activations these belief states, right? And we find it emerge over training. And we found this in transformers. And then we ran this hackathon, and this guy, Keenan Pepper, found the same thing happens in recurrent neural networks. So like, okay, so there is universality to this, that neural networks seem to find these belief states. Okay?
And how are you doing the comparison? If you come in like with the transformation, will it be more business that maps them, or what
So
would you like to do? Yes. Yeah.
you mean just for this
When
one?
you show these different pictures, I'm wondering what is them making similar you find in one transformer or the current neural net? How do you say similar?
Right, so recurrent neural networks, they have hidden states. They have a vector space where there are activations. Like you put in some sequence
Okay.
and there's
And then you
whatever the neural activity is.
Then you have your transformer neutral stream
Yep.
geometric, and then how do you compare those two things?
Right, and then you can say, you can do two different things. The simplest thing is just take PCA of each one, and then you find the same shapes. The other thing that we do is you can do linear regression from that vector space to the anticipated geometry.
Okay.
So again, we're not just saying like, oh, there is an emergent geometry. We're saying it should be this geometry, and then to check that, you can do just a linear regression from there. You find a linear map, and you find it there.
Hopefully, that suggestion would be if you can calculate some variance, like this slope constant protection and entropy rate.
Mhm.
You know that if those numbers are not the same, then the objects aren't the same. It's a very powerful, precise way.
Yeah. Yeah, I mean, I guess there could be some flexibility.
I'm just
Yeah.
arguing for doing information theory on this.
Yeah.
Which-
There could be some flexibility, like for this stuff.
Yeah.
This is in like a 64-dimensional residual stream, so like maybe in other dimensions it does weird
But
stuff.
that's why
Mhm.
the entropy rate and complexity dimension, they are invariants
Mhm.
in any space, whatever the representation is. That's why.
But there might be other stuff going on,
I mean,
I think, right?
You're
Other
talking
stuff?
Like other random noise in other
Right.
dimensions.
I think I'll move on to the quantum stuff.
Yeah. Okay. Yeah.
Sorry,
Totally fine.
just the fact that this work seems to imply that for whatever HMM you choose, if it produces the same process, then there's a linear transformation between the two mixed state presentations that maps them onto each other one-to-one. That's what it would seem to imply. Or that
in
seems like
the geometric representation.
in the geometric representation.
You're saying geometric, I mean, do you have like inner products on these spaces? Are there, what is the
I mean,
geometry?
you just take like Euclidean distance.
Okay, so you're putting, but that's not inferred from the models of you putting that on the space afterwards, or because you're in a real value vector space, you're just saying that you're going to take the Euclidean
Mhm.
geometry?
Yeah, I mean, I think you were making some interesting points yesterday of like, well, there's two things that you're thinking of orthogonal dimensions. Like, there's some, they might have some similarity in the future. So I think it'd be an interesting thing to think about.
Yeah, I mean, I don't want to relate too much, but just the stuff Jim's talking about, like, if we want to actually say these objects are the same in some sense, like, do we mean topologically the same, or do we mean geometrically the same? Yeah, metrically the same, like, and then I think we have to talk about.
Yeah, no, I mean, there's
Yeah.
like a linear transformation from one to the other.
Let me
In
just
the-
emphasize again, so dynamics has spent a long time, half a century, coming up with these exactly the answer to this question.
Mhm.
Do you want to know topological limits? You calculate topological.
Yeah.
entropy.
I'm happy. I'm totally happy for people to
Okay,
do
no, I
that.
just,
So, all right, I'm going to try to tell you a bit about this quantum stuff. So, so I've been working with Tom and Adam on this, and what's the story here? So, there's a way of thinking about this of like, why would hidden Markov models have to do with anything? And one version of telling the story is like, maybe that's a weird restriction. We should just say more general linear transformations. If there's a world model that can use general linear transformations, neural nets can learn that. That's one way of telling the story. But it has an interesting heritage of ideas from frontiers of physics, where people, like I was saying, are saying, oh, well, if you do things with qubits instead of physical bits, or if the world was post-quantum, what would that imply? So what is a physical state? Classically, we might say there's some number of microstates that the world can be in, and we allow ourselves some subjective uncertainty. So you can be like in the convex hull of classical microstates. Okay, then a classical state's a probability vector, basically, over your microstates. What's a quantum state? Well, I don't know, we represent things as density matrices. positive semi-definite self-adjoint trace one operator, which that's kind of a specific thing. So then post-quantum is basically just backing off of that and being like, a physical state is a vector in a real valued vector space, and you basically require that the linear transformations keep you within some convex cone.
I got it. We now have post-classical. Thank you. No, those are GHMMs.
Yeah, no, exactly. That's actually the point. Yeah, it's so these are GHMMs, and so then we say, well,
now I know.
so neural nets should be able to learn GHMMs,
Yes.
and they do,
Yeah.
which is what fine. Yeah.
Good.
So in terms of comparing to the quantum, I mean, the operator is itself not a vector until you vectorize it, in which case its space is n squared. Are you comparing to that operator?
Well, so
That object?
like a density matrix is already a vector in a vector space, but if you want to like vectorize it to have like a column of numbers, there's like a thing you do in a transformation there.
Well, I'm just saying, like in terms of like, you say density is on a space that's size 3, right? If you want to represent it as a vector, it's on a vector space of size 9.
Yeah.
Right.
Yeah, you can say how many linearly independent density matrices are there.
Yeah.
If it's like Hilbert space dimension 3,
Yeah.
then it would be like d squared linearly independent density matrices there.
So just functionally, like if we want to think about like what the transformation would be, or like if you had a quantum state represented in a neural network, it would be as that like vectorized
it would
form.
be in the. I wouldn't necessarily say it's a vectorized form. It's just that the.
I mean, it's represented as a bunch of numbers, right? Not necessarily.
Yeah, I mean, it requires,
structure.
like what's the dimension of the real valued vector space is d squared if we're talking d is the
Yeah.
dimension of the Hilbert space.
Yeah, there's a little problem.
Okay.
Density matrices are not the states of quantum systems. That's what Bobby and I work in, the geometric quantum
Yeah.
systems.
I mean, yeah.
And when you compare those two representations, you see that density matrices throw away, and that changes the geometry and symmetries you get here.
Well, it would be very interesting if there are these different predictions, which one are neural nets learning?
That's a good question.
So let's check.
Okay.
So each one of these kind of classes has an implied, like, what's a state like, what's a linear transformation like. But basically, post-quantum is just basically just linear transformations, and neural nets do this. So there's some recent papers where they talk about these different classes. It turns out that if you have quantum memory or if you have post-quantum memory in the kind of lingo of how mathematical physicists talk about it, the class of stochastic processes that they can generate are different. But the relative advantages, again, is just about being in this real value vector space. There's still something genuinely quantum that could be had, which is composing quantum subsystems, because then your Hilbert space grows exponentially, and neural nets can't really do that, because it's like, again, it's d squared dimensions you need. So if you're composing a bunch of quantum subsystems, you'll quickly outpace. So when I first figured this stuff out, I freaked myself out that we're going to break RSA encryption with neural nets. And I was like, oh crap, like, what do I do? I can't share this work. And then I was like, oh wait, like you would need more neurons than the number of atoms in the universe, so we're fine.
The squared gets you there that fast, or the squared.
It's not the squared. It's composing quantum subsystems.
Oh.
Yeah.
Oh,
Yeah.
It goes up exponentially.
Yeah.
Okay.
Yeah. So,
Right.
so some of you will be familiar with Krauss-Hopper representation of basically what's a general quantum channel like. You can have some quantum memory, and then you put in these kind of two ancillary quantum states. You do a unitary over the joint, and then you can do a projective measure on some ancillary, and you can trash out another one, and that gives kind of the most general form of Krauss operator updating. And these are basically can be interpreted as the classical observations, your measurements, your projective measurements on the ancillary system. But having access to the quantum system here gives you some type of advantage in terms of what types of processes you can see in the measurements. And so then you can think about this in various ways. You can think about this as like a generalized block vector. There's like the block vector for a qubit. So then there's an easy way to see how quantum states are in a real value vector space. But there's lots of different types of representations that you might choose. And again, you don't have to vectorize the thing. So what would belief updating look like? It turns out that you get basically Bayes' rule for quantum and post-quantum states, even though you can't interpret the things. You can't interpret the vectors as probabilities. But regardless, you just work through the linear algebra, and it turns out that you just do Bayes' rule, even though it's not probabilities. And so if you were doing belief updating over a quantum model, then you would do the same sort of thing of like the vector advanced by some subchannel linear operator divided by, well, you'd normalize it, right? And so then what happens is like for some process, so Tom came up with some process because we're like, oh, well, we have classical models, quantum models, sometimes it's fractal, sometimes it's not. Can we make a fractal quantum model? And he's like, oh, okay, so Tom wrote down these Krauss operators, and then that turns out if you write it as a GHMM, then it's that. And then this is showing the belief states of the quantum model. So now instead of in a triangle, which is triangles are classical, quantum, you have circles. So we have fractals in the circle, right? And it's just
You can have them outside the triangles in classical, that's post-quantum. The negative probabilities. Right?
Yeah, quick question. So is this an example where like the constitution of relatives, so you're talking about universality of concepts from the beginning? It's sort of like there's the simplex and then there's a sphere, and you can represent it either way. And so it's kind of like, and there's a
yeah. So it's a bit of a question here of like if we don't have the right framework, if we didn't allow ourselves the quantum representation, then we would be representing pretty fundamentally different.
Yeah,
Right.
they're different symmetries, right? I mean, there's this arbitrary phase that comes up because you're on a sphere, or equivalent of a sphere.
Yeah, but also like
Classical case, it's, you know, it's
but also classically
simplex, so
you
there's a
could
discrete
need,
symmetry.
but also classically maybe you would need infinitely many dimensions. But if you allowed yourself some quantum relaxation, then you have finite dimensions. Yeah.
I'm kind of curious, like, so this what you're representing is in sort of a density space. If you were to put it in the A form, where it's like represented in the vector space,
Right.
what sort of shape would that be?
Those are the geometric quantum states.
So these are the
I don't think so. The geometric quantum states still exist on a block sphere, say if you have a qubit.
Yeah, they're distributions over pure states.
Right.
Sure. Yeah.
But, sorry.
Okay.
sorry, I'm not sure if I get the question, but like with any representation of your density matrix,
Yeah.
Any representation, there's like a linear map from the beliefs over that thing to this, which is so you get the same fractal geometry in each case. So,
Interesting.
Did you figure out if this has to do with hyperbolic space?
what's that?
Did you figure out if this has to do with hyperbolic space? You were talking
Oh,
about
yeah, we talked about this, yeah. Yeah, there's a way in which I see it, but I couldn't like describe it well right now, yeah. So Adam's started some experiments on this where, okay, we have this ground truth belief updating. If you had a quantum model of what the world would be like, and this process would provably require infinitely many classical memory states, but you can get away with basically 2 or 3 dimensions in the quantum setting. And then you train your neural network on, again, just the classical data, and it, over the course of training, this sort of thing emerges in the neural activations, which looks a heck of a lot like what we would anticipate the geometry would be if the model was doing Bayesian updating over a quantum world model.
comment on this is that I feel like what this is showing is that transformers, okay, I don't know if I feel like they might have a lot more shit in them than is revealed by the linear regression. Because I feel like, somebody may have alluded to this earlier, but basically, the linear regression says, this is the right answer, this is what you should be getting, can you get it? So that means they have the information in them to get that right answer. But like, what if they have like a whole lot of other stuff in them, and you can basically pull add like another pressure representation, another pressure representation.
Yeah.
And they get that one and that one and that one.
Yeah, that's a great question. So like, I think before we put this on archive, we have to, I think, do this comparison of like, well, what would a good classical model up to some dimension look like, try to do linear regression to that, and like seeing if, because this stuff is in a high dimensional space, right? So I think you're saying, well, maybe you can just project down onto like all these different representations.
Yeah.
It's a bit of an open question.
Can you just train with a two-dimensional hidden state, or does that not work?
I think it doesn't work because it would just be hard for the model to find the answer. It would, like, just training wouldn't go well.
Maybe you could start with a high-dimensional space, learn this,
and then just like an autoencoder, a good old-fashioned autoencoder.
Sure.
I think also like, you also can just, you can just directly see how many dimensions this lives in.
Yeah.
You can do like SVD.
Right. But I'm saying like if you want to like you can blank the rest of the model,
Yeah,
so you can allow it only to use this and
Yes,
see if it still has
yes.
good performance.
That's right. Yeah. You can
Yeah,
project
so-
the activation standard.
So these
yeah.
are like, I should say, these are like pretty like still preliminary stuff, but we're very encouraged by this, and we're still kind of working out some confusions about it. But it seems to be that models are, and here's just like a different process where over the course of training, the model seems to learn this ground truth. If you look at left and right, this is inside the model after it's done all that training.
These look like circles.
Yeah, well, this for quantum. Yeah. And just to point out, when you do like this GHMM thing, you get the same linear algebra, except now G's instead of T's. It's just the elements of that matrix are not necessarily non-negative, but it's the same linear algebra, and so conditional probabilities are calculated just linear algebraically the same way, and whenever this is the same vector, you get the same prediction, or when vectors are nearby, you get the same predictions over future. So like conceptually, it's not that different at all.
Paul, we should probably wrap up in 5 to 10.
Cool. Sounds good.
Also, I just want to say, really amazing pictures and results.
Thanks.
That's, I mean, the fact that you can represent the belief states, you know, so clearly and visually of a quantum process as well. It's very suggestive.
Yeah, it's very suggestive, and working with Adam and Tom on this has been great because we're like really leveraging our various expertise on this. It's been cool. And yeah, like even just the thing about that you can do basically Bayesian updating on this thing, which is not interpretable as a probability vector, is kind of interesting. And so there's these nice representations of it. Okay, and then there's this, Feniza had this result just in the last year or so, that there's this post-quantum process. So you would require an infinite dimensional HMM to do this, to generate this classical stochastic process. If you try to do it with a quantum system, it would require infinite dimensional Hilbert space, but you can do it with just a few dimensions if you allow more general linear transformations. But it's funny in these papers, they're like, this is post-quantum, and then they write down these matrices, and it's like, matrices aren't post-quantum, like, I don't know, so it's a little funny, this whole thing.
Yeah.
It's like, what would the world be like? And it's like, maybe we're already living in the post-quantum world, so I don't know. But anyway, you change transformers on this process that's like provably post-quantum, and over the course of training, the neural network converges on that representation. So it turns out that transformers, and we believe neural networks more generally, learn quantum and post-quantum representations of the world, if you choose to frame it that way.
There's kind of a duality, right? You're choosing a certain learning algorithm, and then there'll be a class of processes that it can finitely or infinitely represent. And so that's actually what the interest of physics is. That there's a duality between the learning algorithm and the structures you can finitely represent.
Yeah, and the
there's a
learning
hierarchy
algorithm.
of that. So just to say transformers, that induces a whole hierarchy of
Yeah, it's kind of interesting that like the learning algorithm that we're using is just like the standard learning algorithm that people are using. So it'd be interesting to think of like different classes of those. So there's some hint of universality. It's still doesn't answer my grand questions of like what other intelligences would represent things as, but it's hinting that maybe intelligences would represent concepts or at least representations corresponding to the correlational structure of data itself. Maybe this depends on like the tokenization or the lens in which you see the world. Again, these kind of linear functionals of how you look at space-time. But maybe there's something universal. If I'm searching for optimism, maybe there's some hope of like communicating with diverse intelligences. Maybe they would have some sympathy for us because we have some shared representations. Is there something that it's like to be an
Universal, I
LLM?
guess I just was arguing it's relative, it's profoundly relative
Mhm.
to the learning algorithm.
Yeah, maybe.
So to answer the question in an absolute sense, you need to give me a classification of all possible learning algorithms, and then we can talk about what range of representations you can learn from them away. I think those are part of the world. Sorry.
That sounds
Go
hard.
play,
But
go
interesting.
play,
Yeah.
play what
So
you
my time is basically up. So I'm going to flash up
Yeah,
some
go ahead.
questions we can talk about later. Is there something that it's like to be a large language model, which is kind of confusing to me because it's like, well, it only gets to think while you when you prompt it, like maybe during training, but then like when you're using it, then it's like alive. Oh, that seems weird. Maybe there's nothing that it's like to be that. But then you think of like Boltzmann brain arguments and stuff like that. Like, I don't know. What's it like to be an LM? Like, what's it even like to be a human? And part of this is like, well, it's only instantiated when you're doing the thing. But like for humans, what is now? Why do we feel like we have a now? We're extended in the past and present. It has something to do with correlations with past and future. And this kind of depends on different senses, like what's the time scale of now for vision or chemical? Like my biochemistry, my now is quite long. Like if I have coffee an hour ago, that version of now extends for quite a while. Whereas with vision, if I look at a fan, there's some speed of the fan going where it blurs into one thing. So I think that kind of tells me what my duration of now for vision is. When you think about this in all the different senses. And so with my senses, I'm integrated at all these different time scales. And maybe that is something to do with what it's like to be human. I don't know. But I'm wondering a bit in trying to connect with these other intelligences, like who am I? What is my sense of, where do I draw the boundaries? In a way it's fuzzy, in a way, and we're talking about you split the cerebellum and then there's the two of you, so something about strongly integrated, but I have access to the internet, so I stopped remembering things, and so you interact with the things you have access to. Strongly influence what you choose to do, what you choose to prioritize. I care about my family, so it's kind of an extended sense of self. So it's I guess I'm wondering a bit how this plays out. Maybe if AI somehow felt like, oh yeah, we're an extension of humanity, maybe they'd care about us. I don't know. Cyborgism, would I still be me if I vastly grow myself with cyborgism, or then my brain, the gushy part would be some weird appendix, and then it's I don't need that thing. Where are the boundaries of all
You need
this?
the appendix.
I always say that. What's the one? The spool? No.
No, the appendix. We still need it. It's for your microbiome.
Oh, okay.
Even though people take it out.
People get it removed though, and they're okay,
Yeah.
right?
So why do we perceive a classical world? I'm going to suggest because Boltzmann's constant divided by h bar is 131 gigahertz per Kelvin. So let's say at room temperature, you're going to have 4 terahertz is the time scale of coherent oscillations. So people are I don't know, we need to say the world's splitting, many worlds, blah, blah, but actually just the brain's operating at milliseconds, so you'd be averaging over all coherent oscillations that are relevant at thermal energies, that wouldn't get washed out at thermal energies. So I think that's why we perceive a classical world. But is it possible for other intelligences to be genuinely quantum?
Macroscopic, but
Well,
quantum.
I don't know. What's the physical basis of subjective experience? I hope we can talk about that over drinks or even coffee. We can be serious about it. I don't know. And what should I be
Serious? No way.
It's an aspersion.
And what should we be working towards, or what should I be working on? I'm very motivated to understand this stuff, and this is a big question for me right now. What's something worth working towards? And I think we can, with kind of the coming of age of AI, what's a beautiful future worth working towards? I think for me, I'm a scientist, I'm so confused, I'm going to do basic science probably, and hopefully we can have more informed decision making, just to be like, how should we proceed in the age of AI? But maybe something to contemplate, like what research goals are worth it. So thank you.